Greetings, listeners, and welcome to our special 4-part series all about one of nature's most beautiful spectacles, the aurora. Brought to you by Sky at Night magazine and Herta Grutten. Episode 3, the solar maximum. On today's episode of the podcast, I'm talking to Lucie Green, a professor of physics at the Mullard Space Science Laboratory at the University College of London, who studies the sun's atmosphere. Hello, Lucie, and thank you very much for joining us today.
Hi, it's great to be here.
As we mentioned on some of our previous episodes of this series, this year and the next are going to be prime times to see the aurora because our sun's going to be particularly active. But Lucie, why is that?
Well, our sun does follow a natural cycle. So there are times when the sun is fairly quiet. And by that, I mean it's not producing many features on its surface. It's not producing many explosions and eruptions in its atmosphere. And then there are times when the sun sort of wakes up and becomes much more dynamic. And that cycle plays out over about 11 years, roughly 11 years, going from quiet to active, back to quiet again. And as you say, we're now at this very exciting time where the activity is ramping up and the sun is getting pretty busy.
And how do scientists like yourself and other solar scientists actually track what's happening within this solar cycle?
So the main observational way that we can say that there is a solar cycle and where we are in the solar cycle is to look at the sun using visible light. So using a visible light telescope with a filter on it or projecting an image of the sun. And then when you do that, you see what we call the surface, but really it's a kind of visible surface of the sun. And when the sun is not very active, it's basically a blank disk. There's nothing on it to be seen. But then what you notice over the sort of coming weeks and months as you go into the cycle is that these dark spots appear. And we just call them sunspots. So it's not a very imaginative name. They are what they say they are, black spots on the surface of the sun. And they start appearing in small numbers at first, and then that number increases with time. So over sort of 3, 4, 5, 6 years, the number goes up and up and up. So that's looking at the surface of the sun. For people like myself, I'm more focused on looking at the atmosphere of the sun. And we see a corresponding increase in features in the atmosphere of the sun, in particular, hot loops of gas, or loops of hot gas, I should say, million-degree gas in the atmosphere of the sun. And so the atmosphere of the sun is a very hot gas. It's actually threaded by magnetic fields. The sunspots are the footpoints of these magnetic arches, and in the atmosphere we see the actual gas arches themselves. So a solar maximum, sort of as the solar cycle ramps up, we see more sunspots appearing and we see more of these hot gas arches appearing in the atmosphere of the sun.
So we're tracking the sunspots. That's the main sort of visual way that we see it. Is that related to these other kinds of phenomena that you can see? Is there something that's connecting those two? Do they happen to come up at the same time together?
They do. So the phenomena that connects everything in the sun really is magnetism. So I can never talk about the sun without introducing magnetic fields, because the sun, yes, it is this sphere of gas, and probably most listeners will be familiar with that actually. But what's not so well known is that that sphere of gas is threaded and permeated by these very complex magnetic fields. And so in my sort of mind's eye, I picture magnetic fields as, connecting a North Pole and a South Pole. And like if you had a kind of bar magnet and iron filings, you could sprinkle the iron filings around the bar magnet and see these arches going from the North to the South Pole. The sun has that same setup, but the North Pole and the South Pole are represented by sunspots on the surface, and then the lines of force stretch up into the atmosphere of the sun. So the kind of the thing that connects all these layers and that ultimately is responsible for the solar cycle is the magnetic field of the sun and these concentrations where the sunspots are and how that evolves over time.
Now, it's called a cycle, which implies there's some kind of repeatability to it. How regular is this cycle happening?
So each unit of the cycle plays out over roughly 11 years. It is a cycle in the sense that you have times where there are a few sunspots and then the number increases and then the number decreases again. And that repeats. So low, high, low, high, low, high, on and on and on and on and on. But it's not that every unit of the cycle is the same. One cycle can be different to the next. So maybe one lasts 9 years and the next one lasts 13 years. Maybe the peak of one cycle is very high and the peak of another cycle is much lower. So yes, it is kind of cyclical. If you were to plot the number of sunspots that appear on the sun over many years, you would see that number rise and fall and rise and fall. But it's a kind of irregular cycle. So it's not that each one is identical. There's this sort of very intriguing and interesting variation. I think it's interesting that the sun has a cycle in the first place. And then it's interesting that the individual cycles vary. Both of those aspects need to be understood and explained.
11 years, well, to me, it seems like a long time to notice a trend like this. I know we're talking about space, so 11 years is a blink of an eye. But how was it first discovered that this cycle was happening?
So it goes back to observations with telescopes looking at the surface of the sun. And really, that era started, let's say, in the early 1600s, but telescopes developed, looking at the sun became more of interest to astronomers. And so things sort of started to pick up into the 1700s. But the key point in time happened in sort of around 1830, 1840. And that was an era in which some astronomers were thinking about discovering other planets in the solar system. So, for example, Uranus was discovered, and from the sort of peculiarities of the orbit of Uranus, another planet was hypothesized to exist, later discovered as Neptune. When it came to looking at the orbit of Mercury, there were sort of similar inklings that the orbit of Mercury wasn't quite what you would expect it to be, given the science that was known at the time. And so people started to think maybe there's another planet orbiting close to the sun that's causing this sort of intriguing aspect to the orbit of Mercury. And so people started to look at the sun for that purpose. Could you see the black spot of a planet transiting in between the sun and the earth? There was a German pharmacist turned astronomer, Samuel Schwabe, who was interested in finding such a planet orbiting close to the sun and being the person who would discover it. So he set about, every day he had clear skies, he made observations of the sun. So between around sort of mid-1820s into the mid-1840s, he then built up this fantastic catalogue of spots on the surface of the sun, knowing that any new planet would stand out against these spots, which were sort of appearing in their own particular way, whereas a planet would make this repeat appearance in front of the sun. So he was looking for a new planet, but actually when he looked through his vast database and he looked at the numbers of sunspots over time, he realized that the numbers rose and fall in this cyclical way. So he was looking for something else and accidentally discovered the kind of key fundamental character of our sun, which is that it is an active and cyclical star.
I think it's always fascinating when you hear those stories of, we were looking for something else, but we found something that's just as interesting, if not even more so. I always love it when you hear those kinds of things. And so obviously people have been tracking this solar cycle for many, many centuries now. Has it remained fairly constant over that time? Is it fairly predictable?
That's a really good question. And it's the topic of a lot of research that happens around the world. So the cycles vary in size and length, but there are also times when the sun apparently switches off its cycle. And there's a very sort of well-known phase that the sun went through at the end of the 1600s into the start of the 1700s that gets called the Maunder minimum, again after the people who worked on sunspots and realised that the sun sort of almost switched off its activity. So for about 60 years, there were apparently very few spots on the sun. So it's really of interest to try and understand, well, why does this cyclical sun suddenly switch off? But also, perhaps even more importantly, how does it switch back on again? So the sunspots sort of pretty much disappeared, not totally. And there are other signs that the sun was still active during this 60 years. But it's hard enough, I think, to understand how the sun is cyclical, but even harder to know why there are these variations. But it's interesting because there's a whole area of research that, we need to go back and re-look at the records, because do we know that the sun, let's say on a particular day in 1699, did it have no sunspots, or actually was it that nobody was looking and there wasn't a record to say 0 sunspots? So there has been in recent years this sort of global effort to reanalyze historical archives and come up with the kind of best, most accurate record of the sunspot numbers. And that has been a really important piece of work that now we can use to say, okay, we're confident that we have got these times when the sun was quiet for decades, switched back on again. Later on, there were other times when the sunspot cycles dropped quite a lot and came back again. And they're really foundational databases for us.
I think that is an important thing to remember, especially with historical astronomical observations, that a lot of these things were being done by people. There weren't, massive institutes and places like the university that you work for. It was just people individually doing it by themselves. And sometimes they told people and sometimes they didn't tell people as well. So there is a lot of having to go back into the historical records and uncover all of these things. So it's great to hear that there's been a big push to do that again for the solar cycle. But you mentioned at the beginning of the podcast that the solar cycle is very related to the magnetic field of the sun. What can we learn about that magnetic field by studying the solar cycle?
So I think the solar cycle and sunspots are the kind of visible manifestation of the sun having a cyclical and evolving magnetic field. And they tell us things like, how is the magnetic field oriented? Where is the North Pole? Where is the South Pole? And we see that one cycle to the next involves the magnetic poles reversing on the sun overall. So if you imagine like a huge bar magnet inside the sun now with a big North Pole at the top and a big South Pole at the bottom, each solar cycle, they reverse. And sunspots carry the information about that. There's also things like the latitude at which the sunspots form, the tilt that sunspot pairs have. All of these things are really important for us. How the sunspots break apart, how they take their concentrated magnetic field and disperse it across the surface of the sun, how that moves around. So it's because of studying sunspots that we know the sun has a cycle and that we know it's a magnetic cycle and how that magnetic cycle evolves. So they are so, so important. There's a module I teach at UCL, which is solar physics. And the person I used to teach with, Lydia Van Driel-Gastelli, she would always tell the students, when you wake up in the middle of the night, I want you to think about these important rules about sunspots, how they form, where they form, what their magnetic fields are like, because it is the key indicator telling us about the solar cycle. It's so, so important. So yes, we needed to have observations of sunspots, but we need also to be able to measure the magnetic field of sunspots. That became possible in 1908 when the physics was understood how to do this remotely and the telescopes started to be developed to be able to implement that technique. So for the last 100 or so years, we've had the magnetic field information about sunspots, which tells us important information about the solar cycle.
So we've talked a lot about sunspots and how they help us understand what's going on with the solar cycle. But you mentioned that there was other sorts of activity going on. How do we study that? And how does that inform us about the solar cycle?
Because the sunspots are essentially regions of strong magnetic field, they are a kind of reservoir of energy. And that energy gets released sporadically in the form of big flashes of light that we call solar flares and eruptions, literally eruptions of gas threaded with magnetic field that we call coronal mass ejections. So that phrase, it's not very pretty, but it just means ejection of mass from the corona, which is the atmosphere of the sun.
Sometimes you've just got to name a thing after what it is.
Exactly. And some more beautiful language can come later. In fact, another colleague that I work with said that we should call them not coronal mass ejections, but coronal magnetic ejections, because they're this sort of magnetic eruption. But when there are lots of sunspots on the surface of the sun and lots of strong magnetic fields emanating into the atmosphere of the sun from these spots, then you get these heightened times of solar flares and coronal mass ejections. So they're happening more often. And they are essentially throwing out into the solar system lots of high energy radiation like X-rays, ultraviolet light, and these bulk eruptions of material, all of which can come towards the Earth and then slam into the Earth's magnetic field and have a sort of knock-on effect here on the Earth.
So at the moment, we're going through a period of particularly strong activity going on the sun. Where actually are we in our current solar cycle? Where do we fit into the grand scheme of things at the moment?
It's a good time at the moment, good time to be a solar scientist, good time to be someone interested in solar activity and its impact on the Earth, because the sun is active at the moment. We are either at or approaching the peak of the solar cycle. It's a bit hard to say that exactly until we look back in time and we're on the downward phase, because then we can say, okay, that was solar maximum. But definitely we are around the peak. And the peak was forecast to come around sort of 2025. So it's been a slightly larger cycle than was expected. It's perhaps peaked a bit earlier, and that's what happens in larger cycles. But that means that we are seeing a lot of solar flares, a lot of coronal mass ejections, and consequently more displays of the aurora, because it's solar activity, in particular these eruptions from the sun, that drive strong auroral displays that very occasionally then come down to the latitudes that we're interested in the UK. So not just seen up in Scotland, but coming all the way down to the south of England too.
As you expertly said that, this is a special podcast series all about the aurora. So we spoke in the last episode about how the solar wind causes the aurora. How does the solar cycle affect the aurora as we see it on Earth?
So the solar wind is really important because that is a constant outflow from the sun, constant outflow of particles of magnetic field within which the Earth always sits. So it's like a river that sort of washes over us, and the Earth and the Earth's magnetic field is always responding to it. So that's a constant outflow. Now, the fastest streams of solar wind emanate from a particular feature that in the research community we call a coronal hole. That is just a kind of feature that we see in the atmosphere of the sun. Now, at solar minimum, these coronal holes with the fast streams of solar wind are placed at the poles of the sun, so top and bottom of the sun. So they're going in a direction that's not going to encounter the Earth. Towards solar maximum, coronal holes start to form at lower latitudes, and then these fast streams are much more likely to be in the firing line of the Earth, so we're much more likely to experience them. Then in addition, you've got these sporadic bursts of material called coronal mass ejections that race out into the solar system at millions of miles an hour. And when they reach the Earth, they can have a similar effect to the solar wind in that they enhance the displays of the aurora. They make the displays much stronger and push them to lower latitudes. So what we have at solar maximum is the Earth is more likely to be in a fast stream and is more likely to be bombarded by coronal mass ejections. And those two things together mean we're more likely to have strong displays of the aurora.
So it's basically there are more of these events happening, and they also tend to be pointed in the right direction.
Yeah, exactly.
The right time is definitely about now. And what is this particular solar cycle looking in terms of aurora and activity? Is this a particularly good cycle? Is it a weak one? Where are we on that scale?
I'm not sure that I would say it's particularly stand out at the moment. We had in May this year, so May 2024, we had a good Friday night in the UK and in Europe where we had a really fantastic display of the aurora that came down to the south of England. So I stood looking at it from my front driveway and it was fantastic. But it wasn't a kind of standout event, I think, probably a once in a solar cycle event. But what's different now is that we've all got cameras in our mobile phones, so we can take pictures of the aurora. And so actually, when I was stood on my driveway looking at the sky, I could sort of see there was some brightness, but honestly, I'm not sure I could distinguish it from some clouds or maybe some light pollution. It was only when I took a picture, a long exposure picture with my camera, and then I could see the colours, the purpley colours, the reds, stood out green colour. So at the moment, I think I would say we haven't yet had a very large storm, but that's not to say that it's not coming. And this is the hard thing with the sun. It's very hard to say when will we get the really big event that will have a really big impact. But having said that, because we are always in this gusty flow of the solar wind, and in addition to these coronal mass ejections, we do have kind of day-to-day space weather, we would call it, with aurora forming at higher latitudes. But the really big storms are less frequent, and the sun needs to be carefully monitored so that we know when they're going to happen. So this cycle so far, I think, has probably been about what we would expect for a solar maximum, which is still very impactful on the Earth, but it's not had a really standout storm so far.
I have to say, that is one of the things that's I really love about both the sun and the aurora, is so much of stargazing and astronomy is things happening over these huge timescales. You know what's going to happen. You can predict it. You can predict the motion of the planets. But when it comes to the sun and the aurora, you maybe get a couple of days warning. You're just sort of seeing these things as they're happening in real time almost, and following along with them. And I think that's a really magical thing you don't get in a lot of other aspects of space science.
That's a really nice point. And I think it's always worth keeping an eye on what the sun's doing, because you only have, like you say, maybe a couple of days transit time from the eruption leaving the sun to it arriving at the Earth. And what happened in May this year was we had several eruptions take place in quick succession, and they all kind of ploughed into each other and formed this overall enormous structure that then was bombarding the Earth for some extended period of time. And you only really go out and have a look if you start by looking at the sun and seeing what the sun's doing and seeing if it's throwing a coronal mass ejection our way, or if it's got a good fast solar wind stream coming our way because of where these coronal holes are.
Well, thank you very much, Lucy. That has been an absolutely fascinating chat. Thank you so much for joining us on the podcast today.
Good luck with the aurora hunting.
And even though the aurora might be unpredictable and come at a time that you're not expecting, it is possible to record them for posterity by taking a photograph of them. And if you'd like to find out how to take more pictures of the aurora, do tune in to the next episode in this series, where we'll be talking all about how to do that. Goodbye. Thank you for joining us for this episode of our special series all about the aurora. We'll be back soon with episode 4, Photographing the Aurora. From all of us here at Star Diary, goodbye.